Imagine yourself as a chemist in the early 19th century, exploring the properties of different elements. As you observe the similarities among some of these elements, such as their boiling points or their reactivity with other substances, you begin to wonder how to make sense of these patterns and organize the elements in a meaningful way. This question ignited scientific curiosity in the past and led to centuries of research by brilliant minds all around the world. The culmination of this research was the creation of our very own periodic table, an iconic scientific tool that revolutionized the way we understand and study the elements. So, why was there a need of creating the periodic table? In the 19th century, scientists were creating the periodic table to organize the known elements based on their properties and to reveal patterns and relationships between them. At the time, there were only a few dozen known elements, and scientists were struggling to understand their behavior and properties. The periodic table provided a systematic way to organize the elements and identify gaps in our understanding of them. Scientists were also driven by the desire to discover new elements and understand their properties. By organizing the known elements and identifying patterns in their behavior, they could make predictions about the properties of unknown elements and use this knowledge to guide their search for new elements. Overall, the creation of the periodic table was a critical step in the development of modern chemistry, and it continues to be a fundamental tool for scientists who study the properties and behavior of matter at its most basic level. Now, curious about how this remarkable table was created? The modern periodic table that we know today is the result of the work of many researchers who built on the ideas and theories of those who came before them. Some of the most important theories or ideas in the development of the periodic table include Dobereiner's Triads, Newland's law of octaves, Lothar Meyer's classification, and Mendeleev's periodic table. Come along with us on this Class 11 chemistry video, where we will examine the methods used by past scientists to classify elements and how these paved the way for the development of the modern periodic table of elements. In this video, we will delve into the reasons behind the need for classifying elements, as well as explore Dobereiner's triads and Newland's law of octaves in great detail. You may be wondering, why was there a need to classify elements in the first place? The need to classify elements arose from the overwhelming number of elements that had been discovered by the early 19th century. Scientists realized that there was a need to organize these elements into some sort of system to make it easier to study and understand them. By grouping elements based on shared characteristics such as atomic structure, electron configuration, and chemical reactivity, we could make predictions about their behavior and properties. Classifying elements helps in identifying them. Knowing the location of an element in the periodic table can provide information about its physical and chemical properties. The classification of elements has practical applications in many fields. For example, the classification of metals and nonmetals is important in the design and construction of electronic devices. Johann Wolfgang Dobereiner, a brilliant German chemist, is hailed as the first person to successfully classify elements into groups based on their similarities. In a time when the number of discovered elements was growing rapidly, Dobereiner recognized the importance of organizing them into a more manageable system. So let's take a deep dive into Dobereiner's triads and see how they contributed to the development of the periodic table as we know it. Johann Dobereiner noticed that some elements had similar chemical and physical properties and arranged them into groups consisting of 3 elements, known as triads. In every triad, the atomic weight of the middle element was half of the sum of the atomic weight of the other 2 elements. Properties of the middle element were also at the halfway point between both the other elements. For instance, sodium, lithium, and potassium belong to a triad because the atomic weight of sodium is the sum of the atomic weights of lithium and potassium divided by 2, which is 7 plus 39, divided by 2 is equal to 23. These elements have similar properties such as reactivity with water and the ability to form salts with similar properties. Similarly, calcium, strontium, and barium belong to another triad because they have similar chemical properties and atomic weights that follow the same pattern. However, Dobereiner's triads were not successful for every element. Later, it was discovered that this law was not true for all elements. Despite this, Dobereiner's triads were significant because they were one of the first attempts to identify patterns in the properties of the elements. After the failure of Dobereiner's triad, the English chemist John Alexander Newlands gave the law of octaves. Before moving on to the discussion of Newlands' law of octaves, let's quickly summarize merits, demerits, and conclusion of Dobereiner's triads. Dobereiner's triads were one of the first attempts to identify patterns in the properties of elements. One of the main merits of Dobereiner's triads was that they helped predict the properties of unknown elements. Döbereiner correctly predicted the existence of bromine, an element with properties that fit into a triad with chlorine and iodine. Dobereiner's work also laid the foundation for later periodic table development by showing that there were patterns in the properties of elements that could be identified and used to classify them. However, one of the demerits of Dobereiner's triads is that they only applied to a few elements. He only identified 3 triads that included a total of 9 elements. This pattern did not extend to all elements, and it was difficult to apply the triads to elements beyond those 9. Additionally, the triads did not provide a systematic arrangement of the elements, which made it difficult to compare and classify a large number of elements. To conclude, Dobereiner's triads were an important early step towards understanding the periodic nature of elements, despite their limitations. They helped recognize patterns and predict properties of unknown elements, and ultimately led to the development of the modern periodic table. Let us now learn about Newland's law of octaves, a scientific concept inspired by music. Did you know that John Alexander Newlands, the English chemist who gave this law, was struck by the idea that elements might exhibit similar patterns of behavior, just as notes in an octave of music do? So, what is the law of octaves? Newlands proposed that elements can be arranged in ascending order of their atomic weights. And in this arrangement, every 8th element of a row had similar properties to that of the first element of the same row, depicting the octaves of music. Let me explain this in simpler terms. Imagine you are playing a piano, and you play 8 keys from one note to the next note of the same name. The notes will have similar properties, right? That is what Newland's law of octaves says about the elements. John Newland's examination of the 62 known elements revealed a repeating pattern. He arranged the elements in ascending order by atomic mass and noticed that every 8th element exhibited similar properties, which he called the law of octaves. Example: if we start with lithium as the first element, we find that the 8th element from it is sodium, having the similar properties to lithium, and sodium is having the similar properties to potassium. Newlands compared the similarity between the elements to the octaves of music, where every 8th note is comparable to the first. However, there is an important limitation to Newland's law of octaves. It was only true for elements up to calcium, Ca. After calcium, the pattern of similar properties breaks down, and the 8th element of the row no longer has similar properties to the first element. But despite this limitation, Newland's law of octaves was significant because it was one of the first attempts to organize the elements into a systematic pattern based on their properties. Following the unsuccessful attempt of John Newland's law of octaves, Lothar Meyer's classification provided a new system for classifying elements based on their atomic volumes, which helped lay the foundation for the modern periodic table. Before moving on to the Lothar Meyer's classification, let's quickly summarize merits, demerits, and conclusion of John Newland's law of octaves. One of the positive aspects of Newland's law of octaves is that it was the first attempt to organize elements systematically based on their properties. It also provided a foundation for future periodic tables such as Mendeleev's and Moseley's. Additionally, Newland's law of octaves was based on experimental data, not just speculation. One limitation of Newland's law of octaves was that it was limited to only 56 known elements at the time of its development, which was less than half of the total number of elements known today. As a result, the law could not account for the properties of many of the elements that have since been discovered. Another limitation was that the placement of some elements in the periodic table was arbitrary and did not match their actual properties. For example, iron resembles properties of cobalt and nickel, but in Newland's table, iron was placed far away from these elements. Finally, Newland's law of octaves did not recognize the significance of atomic number, which is now known to be a more fundamental property of elements than their atomic weight. To conclude, Newland's law of octaves was a significant milestone in the development of the periodic table, but it had its limitations. Although it provided a foundation for future periodic tables, its shortcomings, such as ignoring the atomic number and arbitrary placements of elements, ultimately made it no longer useful because of new developments. Hope you enjoyed learning about the need of classifying elements, Dobereiner's triads, and Newland's law of octaves in this video. It's fascinating to see how scientists throughout history have attempted to organize the elements and identify patterns in their properties. But the journey doesn't end there. In the next video of this chapter, we will dive into the works of Lothar Meyer's classification and Mendeleev's periodic table. Get ready to discover more about the classification of elements and how it has evolved over time. And now, you should start studying this chapter with the EduRev app as you get video lectures, notes, variety of questions, and MCQ tests for all the chapters of each subject. It's like having the entire school in your pocket.